C11, A, equals 1, 1 plus 1 M11, A, equals 1, 2, equals 2, C21, A, equals 1, 2 plus 1 M21, A
equals 1, 1. C12, A, equals 1, 1 plus 2 M12, A, equals 1, 1, equals 1. C22, A, equals 1, 2 plus 2 M12, A, equals 1, 1, equals 1. 127. Thus, the matrix of cofactors for A is Sig A equals 2, 1, 1, 1. B. The minors of B are M11, B, equals 1301 equals 1, M21, B, equals 0201 equals 0, M31, B, equals 0213 equals 2, M12, B, equals 1321 equals 5, M22, B, equals 1221 equals 3, M32, B, equals 1213 equals 1, M13, B, equals 1120 equals 2, M23, B, equals 1020 equals 0 and M33, B, equals 1011 equals 1. And the CONF factors are C11, B, equals 1, 1 plus 1 M11, B, equals 1, C21, B, equals 1, 2 plus 1 M21, B, equals 0, C31, B, equals 1, 3 plus 1 M31, B, equals 2, C12, B, equals 1, 1 plus 2 M12, B, equals 5, C22, B, equals 1, 2 plus 2 M22, B, equals 3, C32, B, equals 1, 3 plus 2 M32, B, equals 1. C13, B, equals 1, 1 plus 3 M13, B, equals 2, C23, B, equals 1, 2 plus 3 M23, B, equals 0. And C33, B, equals 1, 3 plus 3 M33, B, equals 1. Thus, the matrix of cofactors for B is Sig B equals 152 030 211. Definition 3.24 Determinants of n times n matrix. The determinant of a square matrix A equals I of size n times n, denoted by det A, or A, is defined recursively as follows. If n equals 1, then det A equals A11, otherwise, we suppose that determinants are defined for all square matrices of size less than n and specify that det A equals xn, k equals 1, ak1 ck1, A equals A11 C11, A plus A21 C21, A plus N1 CN1, A 3.1, where Sig A is the I, J, Th cofactor of A. The formula 3.1 is called a cofactor. Expansion across the 1st column of A. Example 3.31. Consider the matrices given in example 3.30. A equals 1 1, 1 2 and B equals 1 0 2, 1 1 3, 2 0 1, 128. The cofactors of matrices A and B, respectively, are given by 2 1, 1 1 and 1 5 2 0 3 0, 2 1 1. Now, using definition 3.24, we have det A equals A11 C11 plus A21 C21 equals 1, 2, plus 1, 1, equals 3, and det B equals B11 C11 plus B21 C21 plus B31 C31 equals 1, 1, plus 1, 0, plus 2, 2, equals 3. Example 3.32. Compute the determinant of matrix A. A equals 1 1 0 0 2 1 1 2 0. A, by expanding the cofactors across the 1 street row. B, by expanding the cofactors across the 1st column. Solution: we have the matrix of cofactors Sig A, given by Sig A equals 2 1 2 0 0 1 1 1 2. A. Now, expanding the cofactors across the 1 street row, we have det A equals A11C11, A, plus A12C12, A, plus A13C13, A, equals 1, 2, plus 1, 1, plus 0, 2, equals 1. B. Similarly, expanding cofactors across the 1st column, we have det A equals A11C11, A, plus A21C21, A, plus A31C31, A, equals 1, 2, plus 0, 0, plus 1, 1, equals 1. Observe that the determinant has the same value for expansions of cofactors across the 1 street row as well American Samoa the 1st column. This is true in general, i.e., the determinant value is the same for the expansions of cofactors across any row or any column. This is briefly stated in the following theorem. 129. Theorem 3.7. The determinant of an n times n matrix A can be computed by cofactor expansion across any row or any column. The expansion across ith row is det A equals xn, J equals 1. Ij A equals AI1CI1, A, plus AI2CI2, A, plus ANCIN, A, equals 1, I plus 1 AI1 plus 1, I plus 2 AI2 plus 1, I plus n. And the expansion across jth column is det A equals xn, I equals 1. Ij A equals A1JC1J, A, plus A2JC2J, A, plus ANJCNJ, A, equals 1, 1 plus JA1 plus 1, 2 plus JA2 plus 1, and plus JANJ. Remark. In Theorem 3.7, if the matrix A, for instance, is of size 3 times 3, then the determinants can be easily computed as follows. I, the expansion across 2 and D row is A equals A21 A21 plus A22 A22 plus A23 A23. 2. The expansion across 3 RD column is A equals A13 A13 A23 A23 plus A33 A33. 3. the sign plus or can be determined using the pattern plus 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 plus. 4. The computation of determinants becomes easier by expanding the cofactors across a row or column with the most 0 entries. Example 3.33. Compute the determinant of matrix A by expanding the cofactors across an appropriate row or column. A equals 1 1 0 0 2 1 1 2 0. Solution. Here, we observe that the 3RD column has more number of 0 entries than any other columns and rows. Thus, the determinant of A, by expanding the cofactors across the 130 3RD column, is given by det A equals a 13 a 13 a 23 a 23 plus a 33 equals 0 1 plus 0 equals 1. Properties of determinants. Let A be the square matrix of size n. 1 if an entire row, or an entire column, consists of zeros, then det A equals 0. 2 if 2 rows, or columns, are equal, then det A equals 0. 3 if one row, or column, is a scalar multiple of another row, or column, then det A equals 0. 4 if A, B and C, respectively, are the upper triangular, lower triangular, and diagonal matrices, given by A equals a 11 a 12 a 13 0 a 22 a 23 0 0 a 33. B equals B 11 0 0 B 21 B 22 0 B 31 B 32 B 33. D equals D 11 0 0 0 D 22 0 0 0 D 33. Then det A equals A 11 a 22 a 33, det B equals B 11 B 22 B 33, and det D equals D 11 D 22 D 33. That is, the determinants of the triangular and diagonal matrices are simply the products of the entries in the main diagonal. Example 3.34. Determine the determinants of the following matrices. A equals 1 2 3 0 0 0 1 2 0. B equals 1 1 0 0 2 0 1 2 0. C equals 1 1 0 2 2 1 1 1 0. D equals 113 113120. Solution: we have det A equals 0, since the entire second row of matrix A consists of zeros. Det B equals 0, since the entire third column of matrix A consists of zeros. Det C equals 0, since the first and third rows of C are equal, and det D equals 0, since the second row of D is a scalar multiple of the first row. Example 3.35. Compute the determinants of the following matrices. A equals 436029003. B equals 300340215. D equals 400060005. Solution: using the properties of determinants, we have det A equals 436029003 equals 4, 2, 3 equals 24. Det B equals 300340215 equals 3, 4, 5 equals 60, and 131. Det D equals 200030005 equals 2, 3, 5 equals 30. Theorem 3.8. For any square matrix A, det A equals det at transposition doesn't alter determinants. Example 3.36. For the given matrix A, verify that det A equals det at A equals 1022111113. Solution: the transpose of matrix A is given by AT equals 1210111213. Now, we have the determinants of A and at R. Det A equals 2, and det AT equals 2. Thus, det A equals det at. Theorem 3.9. Effects of elementary row operations. If matrix B is obtained from a square matrix A by interchanging any two rows, i.e., Ri left right arrow Rj, then det B equals det A. Interchanging. 2. If matrix B is obtained from a square matrix A by multiplying the ith row by a non-zero scalar alpha, i.e., Ri rightward arrow Re, then det B equals det A. Scaling. 3. If matrix B is obtained from a square matrix A by adding scalar multiple of one row to the other, i.e., Ri rightward arrow Ri plus alpha Rj, then det B equals det A. Replacement. Example 3.37. Let A equals 3101011 be the given matrix with det A equals 2. A. If a matrix B is obtained from A by interchanging the first and second rows, i.e., R1 left right arrow R2, then we have det B equals 10131001. 1 equals 2. 132. Thus, det B equals det A. Here, we observe that if the row interchanging has been made 2 times, then det B equals 1, 2 det A equals det A. In general, if the row interchanging has been made n times, then det B equals 1, and det A. Thus, det B equals det A if n is even, and det B equals det A if n is odd. B. If a matrix B is obtained from A by multiplying the second row by 4, i.e., R2 rightward arrow 4 R2, then we have B equals 310404011 equals 8. Thus, det B equals 4 det A. If each row of matrix A is multiplied by 4, then we have det B equals 43 det A. More generally, if A is an n times n matrix, and B is obtained by multiplying each row of A by a non-zero scalar C, then we have det B equals det CA equals C and det A. C. If a matrix B is obtained by replacing row 2, i.e., R2 rightward arrow R2 plus 2 R1, then det B equals 310721001. 1 equals 2. Thus, det B equals det A. Remark. Property 3 of determinants in Theorem 3.9 is particularly more interesting, since it doesn't change the determinant of the original matrix. This property can be used to transform the given matrix into triangular matrix, upper or lower, for which the computation of determinants is much easier than computing the determinant of the original matrix directly, which is tedious and computationally inefficient. Example 3.38. Compute the determinants of the matrices A and B using elementary row operations. A equals 1 1 2 2 3 1 0 1 4. B equals 1 1 2 2 2 3 5 6 1 3 5 3 1 1 3 6. Solution. A. Consider the given matrix A applying the row replacement R2 rightward arrow R2 to R1 and then R3 rightward arrow R3 R2. We obtain the following upper triangular matrix. A equals 1 1 2 0 1 3 0 0 7. Therefore, by theorem 3.9 we have det A equals det A equals 1 1 7 equals 7. 133. B. Similarly, by applying the row replacement R2 rightward arrow R2 to R1, R3 rightward arrow R3 R1, R4 rightward arrow R4 R1. We obtain the following row equivalent matrix. B equals 1 1 2 2 0 1 1 2 0 2 3 1 0 0 1 4. Now, the determinant of the matrix B, by expanding the cofactors across the 1st column and using the determinant of matrix A computed above, is given by B equals 1 1 2 2 0 1 1 2 0 2 3 1 0 0 1 4 equals 1 1 1 2 2 3 1 0 1 4 equals 1 7 equals 7. Therefore, by theorem 3.9 we have det B equals det B equals 7. Theorem 3.10. Product rule. If A and B are two matrices for which the product of is defined, then det AB equals det A det B. Example 3.39. Let A equals 1 2 3 1 and B equals 2 0 1 4 be the given matrices. Then verify that det AB equals det A det B. Solution. Here, we have AB equals 4854, det AB equals 56, det A equals 1 2 3, 1 equals 7, and det B equals 2 0 1 4 equals 8. Thus, det A det B equals 7, 8 equals 56 equals det AB. Definition 3.25. Definition of rank using determinant. Let A be an M times N matrix. Then rank A equals R, where R is the largest number such that some R times R submatrix of A has a non-zero determinant. 134. Example 3.40. Compute the rank of matrix A equals 1 0 2 1 2 3 2 0 using determinants. Solution: observe that the largest possible size of any square submatrix of A is 2 times 2. We have, say, a submatrix 1 0 2 3, which is obtained by deleting the last two columns of A. With 1 0 2 3 equals 3 6 equals 0. Therefore, rank A equals 2. Exercise 3.7. 1. Compute the determinants of the following matrices using elementary row operations. A equals 1 2 3 4, B equals 1 0 2 5 3 1, 2 0 1. 2. Compute the determinants of the following matrices by expanding cofactors across any appropriate row or column. A equals 1 3 0, 1 2 0 6 1 2. B equals 1 3 0 1, 1 2 0 1 5 0 0 0 4 1 1 2. C equals 0 3 1 0 2 0 2 1 0 2 5 1 1 3 3 0 0 1 0 0 4 1 1 0 1. 3. Compute the matrix of cofactors for the given matrices. A equals 1 2 2 3, B equals 1 0 2, 1 1 4 2 0 3. C equals 3 2 1 1. 1 0 2 0 4 1 1 0 3 0 1 0. 4. Determine the ranks of the following matrices using determinants. A equals 1 2 3 0 1 2 1 3 2 4, 1 2 1 3 1. B equals 1 2 0 3 2 1 2 1 0 0 2 1. C equals 1 0 0 4 1 1 2 1 0 0 2 0. 3.8 Adjoint and inverse of a matrix. The inverses of matrices are useful to solve linear systems. In this section, we define the inverse of a matrix. We discuss different methods to compute an inverse, and the properties of inverses. 135. Definition 3.26. Adjoint of a matrix. Let A be an n times n matrix. If Sig A denotes the matrix of cofactors for A, then the adjugate, or adjoint, matrix of A, denoted by adjective A, is defined by the formula adjective A equals sig A T. That is, a joint of matrix A is the transpose of the matrix of cofactors for A. Example 3.41. Compute the adjoints of the given matrices. A equals 1 0, 1 2, and B equals 1 0 2 1 1 3 2 0 1. Solution: the matrix of cofactors for A is sig A equals 2 1 0 1. Thus, the adjoint of matrix A is adjective A equals sig A T equals 2 0 1 1. The matrix of cofactors for B is given by sig B equals 1 5 2 0 3 0 2 1 1. Thus, the adjoint of matrix B is adjective B equals sig B T equals 1 0 2 5 3 1 2 0 1. Definition 3.27. Inverse of a matrix. Let A be an n times n square matrix. The inverse of matrix A is an n times n matrix B such that AB equals in equals BA, where n is the n times n identity matrix. If such a matrix B exists, then the matrix A is said to be invertible, or non-singular, and its inverse is denoted by A1, i.e. B equals A1. A matrix that does not have an inverse is said to be non-invertible, or singular. 136. Example 3.42. Consider the following matrices. A equals 2 3 1 1, B equals 1 3 1 2, C equals 2 3 1 1 2 0 0 0 1. D equals 2 3 2 1 2 1 0 0 1. Then we have AB equals 2 3 1 1 1 3 1 2 equals 1 0 0 1 equals 1 3 1 2 2 3 1 1 equals BA. That is, the products of and BA give us the identity matrix I2. Therefore, matrix B is the inverse of A, i.e., A1 equals B. Similarly, we have CD equals 1 0 0 0 1 0 0 0 1 equals DC. Thus, the matrix D is the inverse of C, i.e., C1 equals D. Theorem 3.11. Let A be an n times n matrix. If A is invertible, non-singular, then det, a, 6 equals 0, and the inverse A1 is given by the formula A1 equals 1 det, a, adjective, a. Example 3.43. Compute the inverse of the given matrix A. A equals 1 0 0 0 2 0 0 0 3. Solution: we have det A equals 6. Sig A equals 6 0 0 0 3 0 0 0 2. And adjective A equals sig A t equals 6 0 0 0 3 0 0 0 2. Therefore, by theorem 3.11, we have A1 equals 1 det, A, adjective, A, equals 1 6 6 0 0 0 3 0 0 0 2. Equals 1 0 0 0 1 2 0 0 0 1 3. 137. Theorem 3.12, Laws of Inverse. Let A, B, C be matrices of appropriate sizes so that the following multiplications make sense. I is a suitably sized identity matrix, and alpha a non-zero scalar. Then, I if the matrix A is invertible, then it has one and only one inverse, A1. 2 if A is invertible matrix of size n times n, then so is A1 and hence, A1, 1 equals A. 3 if any two of the three matrices A, B, AB are invertible, then so is the third. And moreover, AB, 1 equals B1 A1. 4 if the matrix A is invertible, then so is alpha A. Moreover, alpha A, 1 equals 1 alpha A1. V if the matrix A is invertible, then so is at. Moreover, at 1 equals A1, T. 6 suppose A is invertible. If AB equals AC or BA equals CA, then B equals C. Example 3.44. Let A equals 1 1. 1 0 be the given matrix. Then we have A1 equals 0 1. 1 1, and A1, T equals 0 1. 1 1. Now, A, 2A equals 2 2. 2 0 and 2A, 1 equals 1 2 1 2. 1 2 0 equals 1 2 A1. Thus, we have 2A, 1 equals 1 2 A1. B, at equals 1 1. 1 0 and at 1 equals 0 1. 1 1. Thus, we have, at 1 equals A1, T. Computation of inverse using elementary row operations, Gauss-Jordan elimination. Let A be an n times n invertible matrix and n be the identity matrix of size n times n. A equals A11 at 12 a 1 n A21 at 22 a 2 n n1 and 2 n. N equals 1 0 0 0 1 0 0 0 1. Then the inverse A1 can be obtained using elementary row operations as follows. 138. Finding the inverse of a matrix by Gauss-Jordan elimination. 1. Write the n times 2n matrix that consists of A on the left and the n times n identity matrix in on the right to obtain A in. This process is called adjoining matrix into matrix A. 2. If possible, row reduce A to n using elementary row operations on the entire matrix A in. The result will be the matrix in A1. If this is not possible, then A is non-invertible, or singular. 3. Check your work by multiplying to see that A1 equals n equals A1A. Example 3.45. Compute the inverses of the given matrices using Gauss-Jordan elimination. A equals 1 1 3 2, B equals 1 0 0 0 2 0 0 0 3. Solution: let A equals 1 1 3 2. Then we have AI2 equals 1 1 3 2 1 0 0 1 R2 rightward arrow R2 plus 3 R1 1 1 0 5 1 0 3 1. R2 rightward arrow 1 5 R2 1 1 0 1 1 0 3 5 1 5 R1 rightward arrow R1 plus R2 1 0 0 1 2 5 1 5 3 5 1 5. Therefore, the transformed matrix is I2A1 equals 1 0 0 1 2 5 1 5 3 5 1 5. And hence, the inverse of matrix A is given by A1 equals 2 5 1 5 3 5 1 5. Similarly, for B equals 1 0 0 0 2 0 0 0 3. AI3 equals 1 0 0 0 2 0 0 0 3. 1 0 0 0 1 0 0 0 1. R2 rightward arrow 1 2 R2. 1 0 0 0 1 0 0 0 3. 1 0 0 0 1 2 0 0 0 1. R3 rightward arrow 1 3 R3 1 0 0 0 1 0 0 0 1 1 0 0 0 1 2 0 0 0 1 3 139. Therefore, the transformed matrix is I3A1 equals 1 0 0 0 1 0 0 0 1 1 0 0 0 1 2 0 0 0 1 3. Thus, A1 equals 1 0 0 0 1 2 0 0 0 1 3. Exercise 3.8. 1 For the given matrices A and B, compute the adjoint matrices. A equals 1 2 2 3, B equals 1 0 2 1 1 4 2 0 3. To compute the inverse of the given matrix, if it exists. A equals 1 2 4 2, B equals 1 0 2 0 1 2 0 1 3. 3 Compute the inverse, if it exists, of the given matrix using elementary row operations. A equals 4 1 2 3, B equals 1 2 3 1 3 4 1 4 4. C equals 1 1 2 1 0 2 0 0 0 2 1 2 0 3 2 1. 3.9 System of linear equations. Consider an oil refinery that produces gasoline, kerosene, and jet fuel form light crude oil and heavy crude oil. The refinery produces 0.3, 0.2, and 0.4 of gasoline, kerosene and jet fuel, respectively, per barrel of light crude oil. And it produces 0.2, 0.4, and 0.3 of gasoline, kerosene and jet fuel, respectively, per barrel of heavy crude oil. This is shown in Table 2. Note that 10% of each of the crude oil is lost during the refining process. Table 2. Gasoline, kerosene, jet fuel. Light crude oil 0.3, 0.2, 0.4. Heavy crude oil 0.2, 0.4, 0.3. 140. Suppose that the refinery has contracted to deliver 550 barrels of gasoline, 500 barrels of kerosene, and 750 barrels of jet fuel. The problem is to find the number of barrels of each crude oil that satisfies the demand. If L and H represent the number of barrels of light and heavy crude oil, respectively, then the given problem can be expressed as a system of linear equations. 0.3 L plus 0.2 H equals 550. 0.2 L plus 0.4 H equals 500. 0.4 L plus 0.3 H equals 750. The given linear system has three equations and two unknowns. The matrix 0.4, 0.2, 0.2, 0.4, 0.4, 0.4 is known as the coefficient matrix of the system, and the right side of the system is a matrix. 550, 500, 750. With the column vector of unknowns LH, the above information can be organized in matrix form 0.3, 0.2, 0.2, 0.4, 0.4, 0.3. LH equals 550, 500, 750. Example 3.46. Consider the following system of two equations and two unknowns x, y. X plus by equals b1, cx plus dy equals b2. If we interpret x, y as coordinates in the xy plane, then each of the two equations represents a straight line, and x, y is a solution if and only if the point P with coordinates x, y lies on both lines. In this case, there are three possible cases. There exists only one solution if the lines intersect. See Figure 1a. There are infinitely many solutions if the lines coincide. See Figure 1b. And the system has no solution if the lines are parallel. See Figure 1c. 141. X plus y equals 1, 2x plus 2y equals 2, x plus y equals 1, x plus y equals 0, x plus y equals 1, 2x y equals 0. A, C, B. Figure 1. In this figure, A represents the case where the lines intersect, B represents the case where the lines coincide, C represents the case where the lines are parallel. Let us briefly discuss the three different cases. In part A, the linear system is given by x plus y equals 1, 2x y equals 0. This system has only solution, namely, x, y, equals 1, 3, 2, 3. In part B, the linear system is given by x plus y equals 1, 2x plus 2y equals 2. This system has infinitely many solutions. In fact, the point alpha, 1 alpha, is a solution for each real number alpha. And finally, in part C, The linear system is given by x plus y equals 1, x plus y equals 0, which has no solutions, since the expressions in the left side of the two equations are the same, but different values in the right side of the two equations. 142. Definition 3.28. A linear system, or system of linear equations, of m equations in n unknowns x1, x2, x3, xn is a set of equations of the form a11x1 plus a12x2 plus a 1nxn equals b1 at 21x1 plus a 22x2 plus a 2nxn equals b2. m1x1 plus m2x2 plus mxn equals bm. 3.2. Where IGS, for I equals 1, 2, 3, m and j equals 1, 2, 3, n, are given numbers, called the coefficients of the system, and b1, b2, b3, bm on the right side are also numbers. A solution of 3.2 is a set of numbers x1, x2, x3, xn that satisfies all the m equations simultaneously. Matrix form of a linear system. From the definition of matrix multiplication, we see that the m equations of 3.2 may be written as a single vector equation x equals b, 3.3, where a equals a11 at 12 a 1 n a 21 at 22 a 2 n m1 m2 a mn x equals x1 x2 xn and b equals b1 b2 bm are known as the coefficient matrix, the column vector of unknowns and the column vector of numbers, respectively. We assume that the coefficients ij are not all zero, so that A is not a zero matrix. Note that X has n components, whereas B has m components. For the system of linear equations in 3.2, precisely one of the statements below is true. 1. It admits a unique solution. There is one and only one vector x equals x1, x2, x3, xn, that satisfies all the m equations simultaneously. The system is consistent. 2. It has infinitely many solutions. There are infinitely many different values of x that satisfy all the m equations simultaneously. The system is said to be consistent. 3. Has no solution. There is no vector x that satisfies all equations simultaneously, or the solution set is empty, the system is said to be inconsistent. 3.9.1 Gaussian elimination. Gaussian elimination, also known as row reduction, is used for solving a system of linear equations. It is usually understood as a sequence of elementary row operations performed. 143. On the corresponding matrix of coefficients. Consider the linear system given in 3.2. The augmented matrix which represents the system is given by AB equals A11 a 12 a 1 n a 21 a 22 a 2 n M1 M2 a mn B1 B2 Bm. Then, the idea here is, we solve the linear system whose augmented matrix is in row echelon form, which is row equivalent to the original system. And, we have the following theorem on the row equivalent linear systems. Theorem 3.13. Row equivalent linear systems have the same set of solutions. Thus, if the augmented matrix is initially in row echelon form, then we simply solve it by using back substitution. If it is not, then first rewrite it as a row equivalent system whose augmented matrix is in its row echelon form, and then apply theorem 3.13. Example 3.47. Rewrite the following linear system as a row equivalent system, and then solve it. x1 x2 equals 1. x1 plus 2x2 equals 4. Solution. Here, the augmented matrix of the given system is AB equals 1 1 1 2 1 4, which has row echelon form, after a sequence of elementary operations. GAB equals 1 1 0 1 1 1. Thus, the row equivalent system is x1 x2 equals 1 x2 equals 1. Clearly, solving the above linear system, whose augmented matrix is in row echelon form, is much easier than solving the original system. The only solution of the linear system, represented by an augmented matrix in row echelon form, is x1, x2, equals 2, 1. And, hence by theorem 3.13, a vector, x1, x2, equals 2, 1, also solves the original linear system. 144. Gaussian elimination. A. Write the augmented matrix for the linear system. B. Use elementary row operations to rewrite the matrix in row echelon form. C. Write the system of linear equations corresponding to the matrix in row echelon form, and use back substitution to find the solution. Example 3.48. Consider an oil refineries problem which is given as a system of linear equations 0.3 L plus 0.2 H equals 550, 0.2 L plus 0.4 H equals 500, 0.4 L plus 0.3 H equals 750. Where L and H represent the number of barrels of light and heavy crude oil, respectively. The augmented matrix of the given linear system is AB equals 0.3, 0.2, 0.2, 0.4, 0.4, 0.3. 550, 500, 750. Where A equals 0.3, 0.2, 0.2, 0.4, 0.4, 0.3, and B equals 550, 500, 750. And the matrix in row echelon form is given by GAB equals 0.10, 0.20, 0.100. 250, 50, 0. Now, rewriting the given linear system as row equivalent system, we have 0.1 L plus 0.2 H equals 250, 0.1 H equals 50. The only solution of the above system, in row echelon form, is L H equals 1500, 500, which is also a solution for the original system. Thus, an oil refinery needs 1500 barrels of light crude oil and 500 barrels of heavy crude oil in order to satisfy the demand. Example 3.49. Solve the given linear system by using the method of Gaussian elimination. x1 plus 2x2 plus x3 equals 2x1, x2, 2x3 equals 1. 145. Solution: the augmented matrix representing the given system is AB equals 1, 2, 1, 1, 1. 2, 2, 1. Now, by replacing R2, i.e., R2 rightward arrow R2 R1, we obtain 12103, 323. And by scaling R2, i.e., R2 rightward arrow 1, 3, R2, we have 12101121. The last matrix is in its row echelon form, and hence the row equivalent system is x1 plus 2x2 plus x3 equals 2x2 plus x3 equals 1. In this case, the system has infinitely many solutions, and the set of solutions is B given by 1 alpha, alpha, 1 alpha, alpha set membership symbol R. Example 3.50. Solve the following system of linear equations using the method of Gaussian elimination. 4x2 plus 3x3 equals 8. 2x1 x3 equals 2. 3x1 plus 2x2 equals 5. Solution. The augmented matrix of the given system is AB equals 0 4 3 2 0 1 3 2 0 8 2 5. Applying the following elementary row operations, R1 left right arrow R3, interchanging R1 and R3. 3 2 0 2 0 1 0 4 3. 5 2 8. R2 left right arrow R3, interchanging R2 and R3. 3 2 0 0 4 3 2 0 1. 5 8 2. 146. R3 rightward arrow R3 plus 2 3, R1, replacing R3. 3 2 0 0 4 3 0 4 3 1. 5 8. 4 3. R3 rightward arrow R3 plus 1 3 R2, replacing R3. 3 2 0 0 4 3 0 0 0. 5 8. 4 3. The last matrix is in row echelon form, and hence the row equivalent system is given by 3x1 plus 2x2 equals 5. 4x2 plus 3x3 equals 8. 0 equals 4 3. We observe that the last equation in the linear system above is a contradiction to the fact that 0 6 equals 4 3. Consequently, the given linear system has no solution. Theorem 3.14. Consider the system of linear equations in 3.2. If A and B are the matrices of coefficients and the column vector of numbers, respectively, then the following statements are true. If rank A equals rank AB equals number of unknowns, then the linear system has only one solution. 2. If rank A equals rank AB. 3. If rank A. Remark A. From theorem 3.14, we observe that the linear system 3.2 has no solution if an echelon form of the augmented matrix has a row of the form 0, 0, 0 B with B non-zero. B, A linear system has unique solution when there are no free variable, and it has infinitely many solutions when there is at least one free variable. Example 3.51. Use matrix rank to determine the number of solutions for the system. A. x1 plus x2 plus x3 equals 1, 2x2 plus 4x3 equals 2, 2x1 plus 7x3 equals 5. B. x1 plus x2 plus 2x3 equals 3, 2x2 plus 2x3 equals 4, x2 plus x3 equals 2. C. x1 plus 2x2 plus 3x3 equals 1, 2x2 plus 2x3 equals 2. 2x2 2x3 equals 3. Solution 147. A. We have a linear system x1 plus x2 plus x3 equals 1, 2x2 plus 4x3 equals 2, 2x1 plus 7x3 equals 5. And the augmented matrix given by AB equals 1, 1, 1, 0, 2, 4, 0, 2, 7. 1, 2, 5. After a sequence of elementary row operations, we obtain its row echelon form. GAB equals 1, 1, 1, 0, 1, 2, 0, 0, 1. 1, 1, 1. From the transformed matrix, we can see that the matrix A in its row echelon form is AE equals 1, 1, 1, 0, 1, 2, 0, 0, 1. Thus, we have rank A equals rank AB equals number of unknowns. Hence, the given linear system has only one solution. B. We have a linear system x1 plus x2 plus 2x3 equals 3, 2x2 plus 2x3 equals 4, x2 plus x3 equals 2. In this case, the augmented matrix and its row echelon form, respectively, are given by AB equals 1, 1, 2, 0, 2, 2, 0, 1, 1. 3, 4, 2 and GAB equals 1, 1, 2, 0, 1, 1, 0, 0, 0. 3, 2, 0. The matrix A in its row echelon form is AE equals 1, 1, 2, 0, 1, 1, 0, 0, 0. Here, the matrices AE and GAB have only two non-zero rows. Thus, rank A equals rank AB. 148. C. Here, we have a linear system. x1 plus 2x2 plus 3x3 equals 1, 2x2 plus 2x3 equals 2. 2x2 2x3 equals 3. The augmented matrix AB and its row echelon form GAB, respectively, are given by AB equals 123022022 1 2 3 and GAB equals 123011000 1 1 1. Here, the number of non-zero rows of the row echelon form of A and that of AB are 2 and 3, respectively. Therefore, the given linear system has no solution. Exercise 3.9. Solve the following linear systems using the method of Gaussian elimination. A. x1 plus x2 equals 4. 2x1 plus x2 equals 0. B. x1 plus x2 equals 1 x1 x2 equals 0. 2x1 plus x2 equals 3. C. x1 plus 2x2 plus x3 equals 0. 4x1 plus 5x2 plus 6x3 equals 3. 7x1 plus 8x2 plus 9x3 equals 6. D. x1 plus 2x2 plus x3 equals 0. 2x2 plus 3x2 2x3 equals 0. 3.9.2 Cramer's rule. Cramer's rule is a method for solving linear systems where the number of equations and the number of unknowns are equal. Cramer's rule relies on determinants. Consider the following linear system of n equations in n unknowns x1, x2, x3, xn. A 11x1 plus a 12x2 plus a 1nxn equals b1 a 21x1 plus a 22x2 plus a 2nxn equals b2. And 1x1 plus and 2x2 plus an xn equals bn. 3.4. Which has a matrix notation X equals B. 149. Let us define the determinants. D equals A11 a 12 a 1 n a 21 a 22 a 2 n. M1 M2 a mn. dj equals A11 a 12 a 1, j1, b1 a 1, j plus 1, a 1 n a 21 a 22 a 2, j1, b2 a 2, j plus 1, a 1 n. N1 and 2 n, j1, bn and j plus 1, n. 3.5. For j equals 1, 2, 3, n. Here, D is the determinant of the coefficient matrix A, and for each j, dj represents the determinant of a matrix which is obtained from A after replacing the jth column by the column vector B. Theorem 3.15, Cramer's rule. A. If a linear system, 3.4, of n equations in the same number of unknowns, x1, x2, x3, xn, has a non-zero coefficient determinant d equals a, then the system has precisely one solution. This solution is given by x1 equals d1d, x2 equals d2d, xn equals dnd, where d and dj for j equals 1, 2, 3, n are defined in 3.5. b. If the system, 3.4, is homogeneous and d6 equals 0, then it has only the trivial solution x1 equals 0, x2 equals 0, x3 equals 0, xn equals 0. If d equals 0, the homogeneous system also has non-trivial solutions. Example 3.52. Use Cramer's rule to solve the system of linear equations. For x1 2x2 equals 10. 3x1 5x2 equals 11. Solution. Here, the coefficient matrix A and the column vector B, respectively, are 4 2, 3 5, and 10, 11, and the determinants D, D1, D2 are D equals 4 2, 3, 5 equals 20, 6 equals 14, D1 equals 10 2, 11 5 equals 50, 22 equals 28, D2 equals 410, 311 equals 44, 30 equals 14. Therefore, by theorem 3.15, the unique solution of the given linear system is x1, x2 equals d1d, d2d equals 2, 1. 150. Example 3.53. Solve the following system of linear equations using Cramer's rule. 2x1 x2 equals 0. x1 plus 2x2 x3 equals 0. x2 plus x3 equals 1. Solution, with the coefficient matrix A equals 2 1 0, 1 2 1 0 1 1, and column vector B equals 0 0 1. The determinants D, D1, D2 and D3 are computed as follows. D equals 2 1 0. 1 2 1 0 1 1 equals 1. D1 equals 0 1 0 0 2 1 1 1 1 equals 1, D2 equals 2 0 0 1 0 1 0 1 1 equals 2, and D3 equals 2 1 0 1 2 0 0 1 1 equals 3. Thus, by theorem 3.15, the only solution of the given linear system is x1, x2, x2 equals d1d, d2d, d3d equals 1, 2, 3. Remark: Cramer's rule doesn't work if the determinant of the coefficient matrix is 0 or the coefficient matrix is not square. Exercise 3.10. Solve the following linear systems using Cramer's rule, if possible. A. 4x1 2x2 equals 10 3x1 5x2 equals 11. B. x1 plus 2x2 3x3 equals 1 2x1 plus x3 equals 0 3x1 4x2 plus 4x3 equals 2. C. x1 equals 7 2x2 equals 8 3x3 equals 24. 151. 3.9.3 Inverse method. The inverse method is one of the important methods to solve a linear system with n equations in n unknowns. Example 3.54. Consider a linear system. xy equals 1. X plus y equals 3. Using matrix notation, it can be rewritten as 1 1 1 1 xy equals 1 3. 3.6. And if we denote the coefficient matrix by A, then we have A equals 1 1 1 1, and A1 equals 1 2 1 2. 1 2 1 2. Now, multiplying, from the left, both sides of equation 3.6 by A1, we have 1 2 1 2. 1 2 1 2 1 1 1 1 xy equals 1 2 1 2 1 2 1 2 1 3. And using the fact A1A equals I2, we have 1 0 0 1 xy equals 2 1. This implies xy equals 2 1. Thus, x, y, equals 2, 1, is the only solution of the given system of linear equations. This shows the usefulness of the matrix inverse to solve linear systems. Consider the following linear system with n equations in n unknowns x1, x2, x3, xn. A 11x1 plus a 12x2 plus plus a 1n xn equals b1 at 21x1 plus a 22x2 plus a 2n xn equals b2. And 1x1 plus and 2x2 plus an xn equals bn. 3.7 The matrix notation of the linear system, 3.7, is Ax equals b, where A equals A11 at 12 a 1 n A21 at 22 a 2 n n1 and 2 n. X equals x1 x2 xn and b equals b1 b2 bn. 152 Theorem 3.16 Inverse method. If A is an invertible matrix, then for each B set membership symbol Rn, the linear system Ax equals B has a unique solution, which is given by X equals A1B. Example 3.55. Solve the following system of linear equations using matrix inverse method. 2x1 x2 equals 1 3x1 plus 2x2 equals 12. Solution: the matrix of coefficients A, the inverse A1, and the column vector B, respectively, are given by A equals 2 1 3 2, A1 equals 2 7 1 7, 3 7 2 7, and B equals 1 12. Thus, by Theorem 3.16, the only solution of the given linear system is x1 x2 equals A1B equals 2 7 1 7, 3 7 2 7 1 12 equals 2 3. Example 3.56. Use matrix inversion to solve the following linear system. 2x1 plus 3x2 plus x3 equals 1x1 plus 2x2 equals 2x3 equals 3. Solution: the coefficient matrix A, the column vector B and the inverse A1, respectively, are given by A equals 2 3 1 1 2 0 0 0 1, B equals 1 2 3, A1 equals 2 3 2, 1 2 1 0 0 1. Thus, by Theorem 3.16, the unique solution of the given linear system is x1 x2 x3 equals A1B equals 2 3 2, 1 2 1 0 0 1, 1 2 3 equals 2 0 3. Exercise 3.11. Solve the following linear systems using the method of matrix inversion, if possible. A. 3x1 plus 4x2 equals 4. 5x1 plus 3x2 equals 4. 153. B. 4x1 x2 x3 equals 1. 2x1 plus 2x2 plus 3x3 equals 10. 5x1 2x2 2x3 equals 1. C. 3x1 equals 12. 4x2 equals 16. 5x3 equals 20. Review exercises. 1. For every square matrix A, show that A plus et is symmetric. 2. Given matrices A equals 3 0 1 2 1 1, B equals 4 1 0 2, C equals 1 4 2 3 1 5. I. Compute the products A, B, C, AB, C, and verify that A, B, C, equals AB, C. 2. Compute the products alpha, AB, alpha A, B, A, alpha B, and verify that alpha, AB, equals alpha A, B equals A, alpha B. 3. A fruit grower raises 2 crops, apples, and peaches. The grower ships each of these crops to 3 different outlets. In the matrix A equals 125 175 100 175 125. Ij represents the number of units of crop I that the grower ships to outlet J. The matrix B equals $3.50. $6.00 represents the profit per unit. Find the product BA and state what each entry of the matrix represents. For a corporation has 3 factories, each of which manufactures acoustic guitars and electric guitars. In the matrix A equals 70 50 25 35 170. Ij represents the number of guitars of type I produced at factory J in one day. Find the production levels when production increases by 20%. 5. Find the value of X for which the matrix is equal to its own inverse. A. 3x2 3, B. 2x1 2, C. x2 3 4. 154. 6. If A equals cos theta sin theta sin theta cos theta, then I show that A equals A1. 2. Show that N equals cos and theta sin and theta sin and theta cos and theta. 7. If A equals cos theta sin theta sin theta cos theta and B equals cos phi, sin, phi, sin, phi, cos, phi, then show that ab equals cos theta plus phi, sin, theta plus phi, sin, theta plus phi, cos, theta plus phi. 8. Determine the values of alpha for which the matrix A equals 1 1 0 1 0 0 1 2 alpha is invertible and find A1. 9. Show that if A is invertible, then so is AM for every positive integer m. Moreover, AM 1 equals A1 m. 10. If A and B are n times n matrices with A is invertible, then show that A plus B, A1, AB, equals AB, A1, A plus B. 11. Solve the following systems of linear equations using Gaussian elimination. A. x1 x2 plus 2x3 equals 4 x1 plus x3 equals 6 2x1 3x2 plus 5x3 equals 4 3x1 plus 2x2 x3 equals 1. B. x1 2x2 plus 3x3 equals 9 x1 plus 3x2 equals 4 2x1 5x2 plus 5x3 equals 17. C. 2x1 plus x2 x3 plus 2x4 equals 6 3x1 plus 4x2 plus x4 equals 1 equals 2x1 plus 5x2 plus 2x3 plus 6x4 equals 3 5x1 plus 2x2 x3 x4 equals 1. 12. Use Cramer's rule, if possible, to solve the following linear systems. A. x1 plus 2x2 equals 5x1 plus x2 equals 1. 155. B. 4x1 x2 x3 equals 1 2x1 plus 2x2 plus 3x3 equals 10 5x1 2x2 2x3 equals 1. C. 4x1 2x2 plus 3x3 equals 2 2x1 plus 2x2 plus 5x3 equals 16 8x1 5x2 2x3 equals 4. 13. Use matrix inversion method, if possible, to solve the following linear systems. A. 2x1 plus 3x2 plus x3 equals 1 3x1 plus 3x2 plus x3 equals 1 2x1 plus 4x2 plus x3 equals 2. B. 2x1 plus 3x2 plus x3 equals 4 3x1 plus 3x2 plus x3 equals 8 2x1 plus 4x2 plus x3 equals 5. C. 4x1 2x2 plus 3x3 equals 0 2x1 plus 2x2 plus 5x3 equals 0 8x1 5x2 2x3 equals 0 156.
Can I sign up for that one? Waiting is gonna take time.